Alright, in this video what we're going to talk about is we're going to talk about periodic trends based on properties that we've been talking about in this module, which is looking at the electron configurations. So the first periodic trend we want to talk about is the size of the atom. How big is the atom? Now, early on in the semester we talked about the model of the atom. There is a nucleus with a fuzzy electron cloud outside of it. We talked about early on how most of the mass of the atom was at the center in the nucleus, but most of the volume of the atom is outside in this fuzzy electron cloud, which we didn't define very well. And then we've spent the last chapter talking about what does that electron cloud look like. It has s orbitals and p orbitals and d orbitals and shells and subshells and things like that. So the size of the atom is a direct result of its electrons in their orbitals. And so one of the things that we notice is as we go down the periodic table, we look at the atoms as we go down, they are getting more and more shells. Our value of n for our valence electrons our value of n for the electrons that we're adding goes up and up and up. 1, 2, 3, 4, 5, 6, 7th. We're in the 7th shell when we start adding electrons down here, and those shells are getting bigger and bigger and bigger because the orbitals are getting bigger and bigger and bigger, because a 1s orbital is smaller than a 2s is smaller than a 3s, and so on. So as I go down the periodic table, the atomic size increases. This usually happens a lot. This increase in size as I move down is usually a fairly large change. For example, if I were to compare two atoms in a column, let's go down this column. Oxygen is the smallest, sulfur is larger, selenium's even larger, tellurium's even larger, and as I go down I see that the atoms get larger and larger and larger. Again, what I'm doing is I'm adding not only a lot more electrons, but a lot more electrons in the next level, in the next shell. Its valence shell is one shell higher in energy, which also means it's bigger in size. Alright, next let's look at what happens as I consider the size as I move left to right on the periodic table. This one is not so obvious. If I focus, for example, on the elements from boron to neon, what's happening is I am putting one more electron than the previous atom in each of these atoms, but that electron is going into exactly the same subshell as the one before it. Boron's last electron is in the 2p subshell, so boron has one electron in 2p. Carbon has 2 electrons in 2p. Nitrogen has 3 electrons, etc. If I were to look at these electron configurations, I would see that they each go up by 1 in the same subshell, the 2p subshell. As I'm adding those electrons into the 2p subshell, I'm also adding an additional proton at the center of the atom in the nucleus. So I increase the proton at the same time that I'm increasing the electron, the number of electrons. One more proton, one more electron as I move left to right. The net effect of this is that the atoms actually get slightly smaller. As I move left to right on the periodic table, what we find is that the atomic size decreases slightly. That's counterintuitive. You might think, well, I'm adding more electrons, it's got to get bigger. Well, it's not, because the electrons that I'm adding are in exactly the same shell. Even as I move from lithium and beryllium to boron, I'm still in the n equals 2 shell. And I'm also adding another proton to the nucleus to hold on to those electrons. So as I move left to right, the atoms get slightly smaller. Now what you'll notice if you look at an actual table, we can actually measure atomic sizes, and we notice that sometimes there are trends and exceptions, and sometimes two atoms will go slightly out of order. This usually happens as I move from one subshell to the next. Sometimes it gets slightly larger rather than slightly smaller. It also happens when I move from half filling a subshell to going to one more electron than the half-filled subshell. So for example, with nitrogen, I've filled 3 electrons into my 2p subshell. That exactly half fills it. Remember that according to Hund's rule, those individual electrons are in their orbitals spinning in the same direction. That would be the orbital. This would be the valence shell orbital diagram for nitrogen. And then when I move to oxygen, I fill in one more electron into that 2p orbital and pair it up, essentially. And sometimes when that happens, they actually get slightly larger. We can find pictures on the internet with atomic sizes. We see, as we look at this image, for example, that they are getting slightly smaller as I move left to right, but especially as they get down here toward the bottom of the periodic table, I start seeing, yeah, they get smaller, then they kind of get larger, and then they get smaller. We do see that the noble gas is the smallest on the row. Again, you might see a little blips as we move from the third in the P subshell to the fourth in the P subshell. But in general, we do see that they get slightly smaller as I move left to right. We also see the trend on these images that they get larger as I move down the periodic table. So in general, we see that as I move up top to bottom on the periodic table, the atomic size increases. As I move left to right, they get slightly smaller. Next, we'll look at the size of ions. If I want to compare the size of an atom to its ion, for example, let me compare sodium, which has an electron configuration of neon 3s1, to sodium with a +1 charge, which has the electron configuration of simply neon. What I see here is that once the electron is removed to make the cation, the ion is smaller than the neutral species. So sodium with a +1 is smaller than sodium. And it works that way for all cations. The cation of any element is smaller than the neutral element. Another interesting thing is that sodium with a +1 is isoelectronic with neon. We talked about the ions electron configurations. So sodium with a +1 is isoelectronic with neon. It has exactly the same electronic configuration, but they are not the same size. There's a difference between sodium and neon besides their electrons. There isn't any difference in where their electrons are, in what orbitals they're in, but sodium has 11 protons in its nucleus. Neon has 10 protons in its nucleus. So with the same number of electrons, since they are isoelectronic in exactly the same orbitals, sodium with his 11 protons is able to hang on to them tighter and pull them in closer, and so sodium with a +1 will be smaller than neon. In terms of size, the cation is always smaller than the neutral species that he's compared to. He's always smaller than the isoelectronic species that he's compared to. The cation is always smaller once you remove those electrons. If I look at the anion, I see exactly the opposite. Remember that anions are negatively charged, so for example, oxygen looks like helium, 2s2, 2p4. Oxygen with a -2, for example, that's its normal charge, would be helium, 2s2, 2p6, once I add the extra 2 electrons. Adding the extra 2 electrons into his valence shell, but maintaining exactly the same number of protons. He only has 8 protons in either of these cases, means that he gets larger. More electrons with the same number of protons, the anion is going to get larger. The anion will be larger than the neutral species that he is compared to, his own neutral atom. This, you'll notice, is isoelectronic with neon, but it is not the same size as neon. It has exactly the same number of electrons and exactly the same orbitals, but oxygen has 8 protons, neon has 10 protons to hold on to those electrons. Neon is smaller. Oxygen with a -2 is larger than the neutral species that he comes from, he's also larger than the same species he's isoelectronic with. So oxygen with a -2 is actually larger than neon. However, sodium with a +1 is smaller than neon. When I'm comparing two isoelectronic species, the cation is always smaller, the anion is always larger. All right, the last trend we want to look at is ionization energy. Ionization energy is the energy to remove an electron from a neutral atom in its gas state. The gas state is just sort of a technicality, but if I have any atom X, this is the amount of energy, so I usually write it on the left-hand side. It is the amount of energy required to form a positive atom and a free electron. This is a balanced reaction, which writes the ionization energy as part of that reaction. For example, if I have oxygen, let's start with magnesium. Magnesium requires a certain amount of energy to reach in and pull off an electron to become a positively charged cation. We also know that magnesium does not stop at losing one electron. He will normally form a +2 ion in an ionic compound, and so we have what is known as a second ionization energy to remove the second electron from magnesium. Again, it's defined in the gas state, so this would be a representation of the second ionization energy of magnesium. So the first ionization energy, or simply the ionization energy, is the energy to remove that first electron. There is such a thing as a second ionization energy, or a third, or a fourth, or a fifth, as I continue to remove more and more electrons. This amount of energy is always required. We think of this as an endothermic process. It's an amount of energy that must be put into the system. And we can talk about how hard or how easy it is to remove the electron in terms of the atom's size. The ionization energy trend is exactly opposite the size trend. The reason why it is exactly opposite the size trend is because, recall, from valence electron configurations of ions, you are removing the valence electrons. The valence electrons are the outside electrons. And so you are having to reach in and pull off the electron that is farthest away from the nucleus. And the farther away it is from the nucleus, the easier that's going to be. So the easier it is to remove the electron, the smaller the amount of energy, the lower the ionization energy. The easier it is to remove it, the further away it is. So lower ionization energy equates to larger atoms. We see an exact opposite trend. Smaller ionization energies for larger atoms and vice versa. The smaller the atom, the closer to the nucleus you're going to have to reach into to get that outside electron, the harder it's going to be, which means the larger your ionization energy. So, larger atoms have smaller ionization energies, smaller atoms have larger ionization energies. We also can see, remember that once we remove that first electron from magnesium, magnesium with a +1 is actually smaller than magnesium that is neutral. And so our second ionization energy is going to be larger because I'm trying to remove it from a smaller species. And we see that trend on all successive ionization energies. My first ionization energy is always going to be the easiest one to remove. My second ionization energy, it gets harder because the atom gets smaller. My third ionization energy gets even harder or larger because it's getting even smaller as I remove successive electrons. And so we do see that trend.